everyone. I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. We have discussed in our last videos about different types of simple harmonic oscillators, and we have discussed about damped harmonic motion also, and we have considered different cases in case of damped harmonic motion. Today we are going to discuss in detail about forced harmonic motion. And here we are going to see what are the different forces acting on a system which is set into vibration under by applying external force. So what are the forces? Using those forces acting on the system, we'll try to get second order differential equation. And by taking solution for that second order differential equation, we try to consider different cases. So moving further, first we should know what exactly is forced harmonic motion. So what was the damped harmonic motion when we try to compare forced harmonic motion with damped harmonic motion? In damped harmonic motion, what you will observe here is with respect to time, amplitude of vibrations of motion, they are going to decrease slowly and ultimately vibrations are going to die off. Now, whereas in forced harmonic motion, what we are going to do here is we are going to set a system vibrate under the action of external periodic force. So what I'm going to do, continuously I'm going to apply external force to a system. Then obviously what will happen to system? It will keep on vibrating. So here I try to explain two cases. First one is, suppose if you take a simple pendulum and we have displaced our simple pendulum from its equilibrium position, and when we release, then what happens to that system? It will oscillate with natural frequency omega, and these oscillations are free oscillations. And what you will observe here is, in all free oscillations, after some time they die out because there will be some damping forces acting on it. So if we want to maintain those oscillations, then what we have to do, we have to keep on applying some external force. So one good example we can take here, I have taken one very good example in order to understand this forced harmonic motion. Here suppose I have child and the child is moving on a swing. So first one person, he has pushed the swing. So it started oscillating. Now what you will observe here is those oscillations, it will not last for long. Then what child will do in order to continue with its swing movement? What that particular child will do? He will uses his feet in order to maintain that movement of swing. So this is the force being applied by child in order to maintain that movement of swing. So this is one best example in order to understand forced harmonic oscillation. So if you take free oscillating body, eventually after some time its amplitude of vibration is going to die off. But if you want to maintain that vibration, then what we have to do, we have to keep it under the influence of external force. So such type of motion, it is called as forced harmonic motion. So how we can define such forced vibration? It is defined as vibrations with which body vibrate with a frequency, and here because we are applying external force, body it will be vibrating with frequency but not with its natural frequency, and it will be vibrating with frequency under the action of external periodic force. So if we take free oscillations, in that free oscillations body, it will be vibrating with its natural frequency. But here in case of forced vibrations, because we are applying external force, then that body, it won't be vibrating with its natural frequency, but it will be vibrating with some other frequency. So such type of vibrations, they are called as forced vibrations. And always for forced vibrations, we need one external force. And what is the frequency that is given by that external force? That is called as drive frequency. And usually it is represented by P. Now we'll try to get a second order differential equation for forced simple harmonic motion. So what are the forces that are acting on this particular body? First one is restoring force. And here restoring force, again, when your body it gets displaced, then what is the role played by restoring force? It will try to bring back to its equilibrium position. And always we know that restoring force acts in a direction opposite to displacement of the body. And if we try to remove this proportionality sign, we are introducing one constant K, and this constant K, it is called as force constant or spring constant, and how it is defined, force per unit displacement. Okay, and why we are taking negative sign? Because restoring force always act in a direction opposite to the displacement of the body. So this is the first force which is acting on the particular oscillator. Now coming to second one. Okay, once we set a body into oscillation, so there are chances of dampening of vibrations. And why there is dampening of vibrations? Because of some frictional force acting on the body. So this frictional force, it may be more in case of damped and it may be less in case of forced, because our body, it is under the influence of external force. But we cannot neglect this frictional force. We have to take into account this frictional force, and we know that this frictional force acting on the body, it is proportional to velocity. And here if we try to remove this proportionality sign, here we are introducing one important constant, dampening constant. And this dampening constant, how it is given? Frictional force per unit velocity. And again, why we are using negative sign? Because here also frictional force, it is acting in a direction opposite to the velocity. Now apart from these two forces, there is one more force being acted on the body. And what is that force? That is nothing but external force which we are applying to our body in order to maintain vibrations, in order to prevent vibrations to die off. And that external force, it's a periodic force. And how it is given? It is given as F sine Pt. What is F? F is magnitude of force, and P, it is called as driving frequency. Okay, now as usual, we are trying to take these three forces acting on the body and we'll try to compare it with our force which is given by Newton's second law of motion. So according to Newton's second law of motion, what is our force? Force is given by mass into acceleration, and acceleration is represented in terms of displacement as second order derivative. And if I try to balance these three forces with respect to this force, then we end up having expression as, so this is the force because of which comes from Newton's second law of motion, and it is given as, this one is force, that is restoring force, and this one is our dampening force or frictional force, and this is the expression for external force. And I'm going to take restoring force and dampening force to the other side, then we'll end up having the expression like this. Now I'm going to divide whole expression with m. Then I'm going to introduce three parameters. What are those three parameters? R by m, this ratio I'm denoting it by 2b. Then K by M, we are denoting it by omega square. Okay. And then magnitude of force divided by mass, it is given by small f. And if I'm going to substitute these three in my differential equation, I'll have simplified form of differential equation as d square x by dt square plus 2b dx by dt plus omega square x is equal to f sine pt. So this is the differential equation for forced harmonic motion. Now next we are going to see what can be the different cases we can consider from this second order differential equation. But for that, what we need to do, first we need to find solution, and from that solution we are going to get expression for amplitude of vibration and also what is the phase maintained between the displacement and as well as the applied force, displacement of the body with respect to the applied force. Now what you will observe here is, so we have a body which is set into vibration under the influence of external force. And when we say that the body, it has reached steady state when body starts vibrating with frequency of periodic force, but not with its natural frequency. And solution for second order differential equation, I am taking it as A sine Pt minus T. Of course, A is steady amplitude of vibration, and P is our driving frequency or the frequency of external force applied. And here there is one parameter theta. What is our theta? Theta is the phase angle. And what is that phase angle? It is the phase difference between displacement and applied force. So by taking this equation, we'll try to get expression for both amplitude steady state amplitude of vibration, as well as we try to get expression for theta, and from those expressions for amplitude and phase angle, we'll try to figure out what are the different conclusions we can take. So we have our displacement here. Now I have my differential equation. So what differential equation we got? D square x by dt square plus 2b dx by dt plus omega square x is equal to f sine pt. This is the second order differential equation we got. Here I have d square x by dt square as well as dx by dt. So I'm going to differentiate this expression for displacement once and then twice. So if I differentiate it once, I'll get like this. And then if I differentiate it twice, we end up having this. And I'm going to substitute these two values in second order differential equation. And after substituting, so once we substitute these expressions, so what I have done in place of d square x by dt square, I have substituted this value minus ap square sine pt minus theta plus 2b is there as it is. And in place of dx by dt, I am substituting ap cos pt minus theta plus omega square x is equal to f sine pt. And this sine pt, I am writing it as sine pt minus theta plus theta. So there is no harm in writing like this. So I'm writing it like this. And in next expression, what I have done in place of x, I have written expression for displacement as a sine pt minus theta. And this is in the form of this particular expression. It is in the form of sine a plus b. And we know that sine a plus b, it can be written as sine a cos b plus cos a sine b. So this we can write like this. So if I try to write it, so this is our A and this is our B. So if I write, I can expand it like this. Now after that, what I'm going to do, here I have sine pt minus t and here also sine pt minus t. If I take out common, then here in brackets, I have minus ap square plus a omega square plus 2b ap cos pt minus theta. And here I have this expansion. Now I'm going to compare left hand side with right hand side. If I compare, as you can see here, first I'm comparing coefficients of sine pt minus theta. So what you will get here on left hand side, I have minus ap square plus a omega square or a into omega square minus p square. And what we have on right hand side for coefficient sine pt minus theta, it is f cos theta. And then next, I'm trying to compare coefficients of cos pt minus theta on both left hand side and right hand side. Then 2abp is equal to f sine theta. Now I'm going to make use of these two expressions. First, in order to find expression for amplitude, I'm going to square these two equations and then add. So when I square and add these two equations, when I square first equation and add these two equations, then what we have, a square into omega square minus p square whole square plus 4a square b square p square is equal to f square. So because on the right hand side, why we'll get f square? Because this will become f square cos square theta, this will become f square sin square theta. If we add, we'll have cos square theta plus sin square theta, it is equal to 1. And we are squaring this and we are squaring this and then we are adding. So that is there on the left hand side. Now from this, if I rearrange the terms, I end up having expression for amplitude like this. So this is our expression for amplitude of vibration in case of body which is undergoing forced vibrations. This is and next, in order to get expression for force difference between displacement and applied force, I'm going to divide this equation. I'm going to divide sixth equation with respect to phi. Then what I'll have, tan theta is equal to this, and from theta I'll have this expression. So these are the two important expressions. From this we are going to make very important conclusions. Now, what are those conclusions which we can draw from these values? Now if you see here, so here depending upon the relative values of p and omega, I'm trying to compare two frequencies here. What are those two frequencies? One is frequency of applied force, which is called as driving frequency. Why it is called driving frequency? Because it is driving or it is making our body to oscillate. And omega, Omega we can call it as natural frequency of vibration of the body. So depending upon these relative values of driving frequency and natural frequency, we are going to get three cases. So what are those three cases? First case, what I am saying here is when the driving frequency is low. So here driving frequency is low. The frequency applied by external periodic force is low, or natural frequency of vibration of the body is more. Then what happens to our amplitude of vibration as well as phase difference? And what formula we have for amplitude of vibration? F by square root of omega square minus p square whole square plus 4b square p square. This is the expression we got for amplitude. And theta, it is given as tan inverse 2bp by omega square minus p square. So this is the expression we got for omega square minus p square whole square. So here now my p is very, very less. So this p is very, very less. I am going to neglect this p with respect to omega. So here I have omega to the power of 4. And this again omega to the power of 4 term, it will be very large compared to this 4b square p square. So for simplicity's sake, I am going to neglect this term. Then you end up having square root of omega square whole square. So omega to the power of 4. If I take out square root, then I end up having my a to be f by omega square. So here, what is the expression we got for amplitude? Amplitude is f by omega square. But what is our f? F is equal to f by m. And what about our omega square? Omega square is our, it is given with respect to spring constant k by m. So we end up having this as f by k because m will get cancelled. So here you will observe that when your driving frequency is very low, then amplitude of vibration, it depends upon the magnitude of force. So it depends upon how much force you are applying. So based on that force, the amplitude of vibration will be there. And also it is dependent on the force constant k. So here what you will observe here is at lower frequency of the external force, amplitude of vibration will increase. So this is very important point. Now coming to phase difference. Now we have this formula for phase difference and we are saying that P is very less compared to omega. So P is very less compared to omega. So here omega is very large and here P is very less. So this approximately I can take it to be very small value or I can take it to be 0. And tan inverse of 0 is 0. It means that both the displacement and applied force, they are in phase. So when your driving frequency or frequency applied by external force is very, very small, then displacement of the body and applied force, both of them will be in phase. So this is the first conclusion. Then coming to second conclusion. So what is our second conclusion? Second conclusion is when we are at resonance. What is the resonance? When frequency applied by external force and natural frequency of the body, if both of them are same, then what will happen? Now again, I am writing expression for amplitude, which is given like this: f by square root of b square minus omega square whole square plus 4b square p square. And then our phase difference, it is given as tan inverse of 2bp by omega square minus p square. Now my omega and p are 0, so this will get cancelled. So this, you will have this as amplitude as A is equal to f by 2bp. So actually this is small f by 2bp. But what is our f? F is small f, it is written as f by m, and this 2b is r by m into p. So this we can write it as f by r p. But what is our p? P is omega, so f by r omega. This is what we'll get here. So this is the expression we are getting for amplitude. Now what conclusion we can take from this? amplitude of vibration is inversely proportional to factor R. What is factor R? It is the damping factor. So your amplitude depends on damping factor R. So because they are inversely proportional, if your damping is small, then amplitude will be very larger. Then coming to this phase difference, because your omega is equal to P, so here you will end up having 0. So anything by 0 will be infinity, and tan inverse of infinity is pi by 2. So what is the phase difference between displacement and force? It is equal to pi by 2. Then coming to a third case, what happens when driving frequency is very much higher than the natural frequency of the body? When we have increased the driving frequency and we have gone to higher frequency values, then again writing expression for amplitude. What is our amplitude? F by square root of b square minus omega square whole square plus 4b square p square. And our phase difference, it is given as tan inverse of 2bp by b square minus omega square. So here we are saying that our p is very much large. Sorry, this is omega square minus omega square minus p square. So in this case also omega square minus p square. Okay, and here our p is very, very large. So I can neglect this omega. So I'm going to neglect this omega. So here I have p square, and here I have p to the power of 4. So here what you'll observe here is even. So ultimately you end up having this as f by p square. And what about our phase difference? Because our p is very, very large, so omega is very small compared to p. So it means that my value, it will be minus 0. So because in the denominator I have very large value, so small value by large value, we can approximately take it to be 0. So it is minus 0. And when we take tan inverse of minus 0, we have 180 degrees. Now what does it indicate? It means that when we go for higher frequencies, higher values of driving frequency, what is happening to amplitude? Amplitude is decreasing. Okay, and what is the phase difference between the displacement and the applied force? It is equal to 180 degrees. Now I'm going to consider all these three cases, and I'm going to see how the amplitude of forced vibration is dependent on driving frequency. That we are going to show in this particular figure. So what we have done, on x-axis we have taken frequency of external force, that is nothing but driving frequency. On y-axis I have taken amplitude of vibration. Now what you are observing here is, here we have taken three curves. So here, first case, when damping factor is very, very small, when we have medium damping, and here we have heavy damping. Now first, forget about damping. Suppose I have taken this curve. Now what you are observing here is at lower driving frequency. What do you mean by lower driving frequency? When your P is less than omega, that is our case 1. So what is happening to amplitude? Amplitude is increasing. That is the first conclusion we got when we have taken P less than omega. Now, whereas when P is equal to omega, what we have observed here is, when P is equal to omega, your amplitude, it goes to its maximum value. And then when P is very much greater than omega, when we go for higher frequencies of applied forces, what is happening to our amplitude? It keeps on decreasing. So at lower frequencies of external force, amplitude is increasing, and it goes to very high value, infinity value, when we are at the condition of resonance, where frequency of vibration of body is equal to frequency of the applied force. And beyond this particular resonance, when we go for higher frequency of external force, what we will observe that amplitude of vibration is going to decrease. And one more thing what we have to understand here is, when we go for small damping, our curve is sharp. At resonance, you will have sharper curve. So smaller is the damping, sharper is the resonance. Whereas higher is the damping, what is happening at resonance? Our curve is getting flatter. So larger is the damping, flatter is the resonance. So these are the conclusions which we have drawn. So first conclusion, what we are saying here is, when there is no damping, So when there is no damping, when we are at very low frequencies of external force, then what is happening? Amplitude is increasing with P. And at resonance, what is happening? It goes to maximum value infinity, and beyond omega, what is happening to amplitude? It is decreasing with driving frequency. And we have seen that for smaller damping cases, resonance will be sharper, and whereas for larger damping, resonance is flatter. And what we have observed here is, as you can see, when damping is increasing, what is happening to amplitude value? It is decreasing. So you'll have larger amplitude value for smaller damping systems. So this is what we have discussed about forced harmonic oscillations in this video. I'm going to stop my video here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.